so navigation planning, in essence, takes us from point A to point B, and the simplest way to get from point A to point B is a straight line. But what if we're not interested in the simple straight line? Let's say we have this case where we're turning a corner. Ordinarily, in the field of robotics, people would use something like Dubbin's curves or some sort of trajectory that minimizes distance, for example. Well, that's all well and good, except for the fact that that does not guarantee smooth curvature. And if we're in the business of autonomy, we want to make sure that our autonomous vehicle, in turning that corner, will have a perfectly continuous steering command. We can't jump, we can't have discontinuities. And we achieve that precisely by composing our paths as combinations of straight segments, clothoids, and circular arcs. And that achieves this desired smoothness in curvature. Perfect. Now, how do we pick the precise curvature? So I've given you a family of curves. How do we know which precise curve to pick? Well, we explore a very large search space, and we have algorithms that do that. Particularly, we have the A-star algorithm. So you can see here a big family of curves, and A-star goes through those very systematically and tells us what the optimal curve is. Now, let's consider the constraints on arrival and departure. If we are not constrained in the orientation of the vehicle on arrival or on departure, we say we're going from a point to another point. If we're constrained on arrival, we say that's a point to a line. And then similarly, we have a line to a point and then a line to a line. And you can think of these four basic movements as the building blocks of more complex maneuvers. Now, speaking of complex maneuvers, one of the most complex maneuvers that we encounter when doing path planning for autonomous systems is the end of a row. So what you do when you reach the end of a row depends on your vehicle and your particular application. So let's start with the simplest case. You are in your car, you do a U-turn. Autonomous systems can also do U-turns, and we call that a free turn. Here in the bottom, we're showing you what these turns actually look like from in-cabin apps. So what you're seeing down there, it's a cartoon, but what you see right here, that's an actual implementation of these turns. Okay, the problem with that free turn is that it takes up a lot of space. That green band is very broad. How can we improve upon that? Well, let's say we defined a much narrower band around the edge of our area, and we call that a headland, and that headland has a center line. If we constrain the vehicle to turn following that center line, that headland line, we call that a headland following unidirectional turn. But what if the tracks are very narrow for the turning radius of your vehicle? In that case, we can engage in what we call a two-point turn, where you go on the headland, and then you engage the next track in reverse. So of course, that's a lot more efficient for narrow turns. But what if you can't engage the next track in reverse? Well, then we go one step further, and we end up with a more complex turn that we call a three-point turn. There, you're only engaging the headland in reverse, but whenever you're on your tracks, you're going forward, which is great. And now to sum this all up, here we have a real example. We have a vehicle pointing down at the start point. That's the outline of the vehicle in yellow. And it needs to be pointing down at the end point. But there's an obstacle in between. So if you invoke our path planning libraries, this is what you're going to get. Going from A to B, considering the obstacle, considering the curvature of the path, and considering the desired orientation.